Hi everyone. In this practice hackathon, my goal is to build a classifier to predict loan outcomes, and the metric we care about is the FE score. I'm using FE because the classes are imbalanced, and FE balances precision and recall, which is more meaningful than accuracy for this type of loan problem. In this video, I will cover these three things: the key processing and modeling steps, and how I am prove the performance, how I assess the model fit and the reliability, and what I would do next with more time and resources. First, I build an end-to-end pre-processing pipeline to avoid data leakage and to ensure the same transformation are applied consistently to train and test data. I automatically separated features into numerical and categorical columns. For numerical features, I handle missing values using median imputation and then standardized the features. For categorical features, I use the most frequent imputation and warm-hot encoding, and I set the encoder to ignore unknown categories so the model can safely handle categories that appear in the test set but not in the training set. After pre-processing, I compared at least three models using stratified cross-validation and evaluated them with FE. Logistic regression with balanced class weight achieved an FE of about 0.74. Balanced random forest achieved 0.81, and his Guardian boosting baseline performance best at about 0.83. And this comparison suggests that the patterns in data are not purely linear, since the logistic uh, regression is much weaker, and that tree-based model can capture non-linear relationships and interactions better fit for this problem. Based on these results, I choose his Guardian boosting as my main model. To improve performance further, I run hyperparameters turning using random sized search CV on the HIST Guardian boosting pipeline. I termed key parameters such as learning rate, maximal depth, number of boosting irritations, minimal leaf size, and the regulations. And I use stratified cross-validation inside the search to get a stable estimate of performance. After turning the best cross-validation, FE within the training split reached about 0.84, which is an improvement over the baseline model. Because the final classification decision depends on the probability throws. I also performed the throws holding turning instead of using the default 0.5 cutoff. I use a holdout validation split and a surge across threshold to directly maximize FE. The best threshold I find was 0.360, and at this threshold, the holdout FE was about 0.835. The three the threshold versus Fe curves shows a clear peak of around 0.36, and the performance drops if the threshold becomes too low or too high, which confirms that choosing the threshold is an important step when the objective is Fe. To assess model fit and reliability, I used two layers of validation. During model comparison and hyperparameters turning, I use the stratified k-fold cross-validation to reduce variance in the performance estimate and preserve the class ratio in each fold. After selecting the model, I use a separate holdout set for threshold turning to avoid over optimizing the threshold to the cross-validation folds and to better simulate a realistic validation scenarios. I also plotted a learning curve for the turn the best model. Using FE score, the learning curve shows that the training FE stays higher than cross-validation FE and F1, and the cross-validation curve increases as training size grows and then starts to flatten in the low 0.83 range. This indicates the model is learning meaningful signal and generalized reasonable well. But there is still a gap between training and validation that suggests some overfitting. The upward trend is the validation curve also suggests that adding more data could further improve generalization. Next, I evaluate the model's classification behavior using a confusion matrix at the term the threshold of 0.36. On the holdout set, the confusion matrix shows 5,292 true negatives, 308 false positives, 232 false negatives, and 1,368 true positives. In a norm context, these errors have different business impact. A false negative means predicting a browser is safe when they actually default, which can lead to financial loss. A false positive means predicting default for someone who would repay, which rejects a good customer and reduce revenue and customer satisfaction. Threshold turning helps manage this trade-off to align the decision rule with F1 and with practical risk versus growth considerations. Finally, I review the precision recall curve, which is especially informative for imbalanced classification. The PR curve shows how precision decreases as recall increases, meaning that if we try to catch nearly at all positive cases, we will usually sacrifice precision and generate more false positives. This visualization supports why selecting a threshold based on F1 can provide a balanced operating point rather than pushing too far towards only precision or only recall. If I had more time and the resources, I would improve the model in two main ways. First, I would add external datasets that are known to be predictive for credit risk, such as microeconomic indicators like unemployment, inflation, and interest rates aligned to the relevant time periods. If available, I would also incorporate credit bureau style features such as credit utilization, um, del- delinquency history, recent credit inquiries, or credit score band. Since these often deliver significant performance gains in default prediction. Second, I would plan for production monitoring and drift detection in deployment. I would monitor precision, recall, approval rate, and observe default rate over time. And I would check feature distribution drifting using tools like PSI or statistical tests, as well as monitor prediction probability distribution if drift is detected. I would trigger investigation and potentially retrain the model or on more recent data or recall, recalibrate the decision threshold while maintaining model versioning and a rollback strategy for safe updates. To conclude, I built a leakage-safe pre-processing pipeline, compared these models using F1 and uh, stratified cross-validation, selected histoguardian boosting as the best performing baseline, improved performance through randomized hyperparameters tuning, and optimized the final decision threshold to maximize F1. I assess the fit using cross-validation, learning curves, and the diagnosis plots such as the confusion matrix and the precision recall curve, and I interpreted the results in terms of real-world law decision trade-offs. Thank you.